Hi everybody, I hope you're all well. I hope you had a nice weekend. Well, as nice as you can possibly have in these current times. So today is going to be some note taking, but you will need to get some paper. And what I'd strongly suggest is that you copy all these notes out. There'll be very little else to do from the book today. I want you to copy them out and insert them into your notes as an attachment. What I've written out here and on the next few pages really needs to be part of your notes, okay? Because it goes through some important stuff where the notes I don't think are quite up to it. Now, the first bit recaps what we already know. So we've got a function f of x equals x cubed minus 2x squared, take x add 2. If we find dy by dx by differentiating once, and then solve that equal to 0, we can find the stationary points, as you know. So we've got stationary points here, x equals 1.54, x equals minus 0.22. The function is increasing if we solve dy by dx is greater than 0, and it's decreasing if we solve dy by dx is less than 0. So I've put together this sketch. The roots are at minus 1, 1 and 2. Got a stationary point at minus 0.22, I've got a stationary point at 1.54, got y-intercept at 2. Now you can see that all here until it gets to the 0.22 that we are increasing. Then between minus 0.22 and 1.54 we're decreasing, and then when the x values that are bigger than 1.54 will give us positive gradient. Now the second derivative is it's the expression you get when you differentiate the first derivative. So we've got original function, dy by dx is to differentiate once, d2y by dx squared is to differentiate twice. Okay, so you can see that that is the first derivative differentiated. And given that the dy by dx is the rate of change, okay, i.e. the gradient, that if we differentiate the gradient function, we're getting the rate of change of the gradient. So if the rate of change of the gradient is negative, that must mean that the gradient is decreasing, i.e. going from something steep to something less steep. Okay, so here we've got the gradient decreasing, and that's where the second derivative is less than 0. Now, this is known as the curve at these times is, we call it concave. If the second derivative d2y by dx squared is greater than 0, that must mean that the gradient is increasing, and that means that it's going from a less steep gradient to something steeper, and the shape of the curve has something like this. Okay, so you need to recognize these two shapes. If it's going up like that over, or if it's sort of arced like that, one is concave and one is convex. Okay, now the point where a curve goes from being convex to being concave, or vice versa, is called a point of inflection. Okay, now just a heads up, there are two things here. There are points of inflection where a curve goes from being concave to convex, like we have here. Here, hopefully you can see that this is a combination of the two types of curve. Convex going to concave, and at the instant that that happens, we have a point of inflection. We must be very careful to not confuse a point of inflection with a stationary point of inflection, which is something I'll talk about soon. But for now, the point where a curve goes from being convex to concave or vice versa is called a point of inflection. Okay, so to summarise, if you are interested in the range of values for which a curve is convex, that is for the x values that come from this inequality. Okay, so the range of x values for which the second derivative is negative is the range of x values for which the curve is concave. to find the range of values for which a curve is convex, we would solve the second derivative greater than 0. And the range of x values that we get from that is the range of x values for which the curve is convex. To find the point of inflection, solve the second derivative equal to 0. So this is considering the moment where we go from negative to positive, and in that instant the second derivative is 0. So to find the point of inflection, i.e. where it goes from concave to convex, we solve the second derivative equal to 0. To find the range of values for which we are concave or convex, we solve these two inequalities here. Okay, now we move on to, it says may have to prove this. The example will get into that, so don't worry. The stationary points and the second derivative. The second derivative, based on what we've just talked about, will enables us to not only identify the coordinates of the stationary points, but we can also use the second derivative to determine whether we have a maximum point or a minimum point. Now, if you think about what we've just talked about, so if the second derivative is negative, that must mean that the gradient is decreasing, and we've got something like this. If it continues to decrease, it must get to 0, and it must then continue to get smaller. And in these dotted lines here, these dotted dots, that's where we've got negative gradient. We had previously had positive, but because the gradient was decreasing, because the gradient was decreasing, it's got smaller and smaller and smaller till it's gotten to 0, and it was carried on to decreasing. So, in a nutshell, if you find where your stationary points are, substituting in the x value of the stationary point into the second derivative will allow you to decide if we've got a maximum or a minimum. So if the second derivative is negative for a value of x where dy by dx equals 0, i.e. the x value of a stationary point, that indicates a local maximum. Okay. If we substitute an x value from a stationary point into the second derivative and it's positive, then it must mean that we have a local minimum. And here we've got it getting, it's got a positive gradient, it's got a negative gradient, but it's getting shallower and shallower and shallower, and then it continues to increase, and then we have positive gradient. And so in the middle, there is the stationary point. But to be honest, you never have to prove that. It's just, if you're asked to determine the nature of a stationary point, you will substitute the x value of the stationary point into the second derivative and make a decision based on these results as to whether we've got a minimum or a maximum. Now, I want to go back to the examples in the notes to finish off one or two of those, just to put this into place. But we'll do that in a bit. Now, the third instance, okay, and this is where it becomes a bit confusing. The third possibility is that we substitute a value of x where we have a stationary point into the second derivative and we get 0. So if that happens, it may be the case that we have a stationary point of inflection. Okay, now this isn't where the graph is going from convex to concave. This is where it has a 0 gradient, but it doesn't loop back the other way. So we've not gone from a positive gradient stationary point to a negative gradient to create a maximum. We've gone positive 0 gradient back to positive, and it's that you've seen these on, say for example, the graph of y equals x cubed. It's this that is a stationary point of inflection, and here there is further investigation required. Okay, so the examples will show you what that's about. So in a nutshell, you find the stationary points, you substitute the x coordinate of the stationary points into the second derivative. If the answer you get is negative, you've got a maximum point. If the answer is positive, you've got a minimum point. If it's 0, it may be a maximum or a minimum, but it might be a stationary point of inflection, and this is why we have to do some further investigation. So that's basically summarised there, and I'm just going to pause it for you to, well, you can just copy out those notes. Next video we'll be going through the 2 examples, and so you can see this all put into action.